Here we are with part 3 of our introduction to mass spectrometry as part of the analytical biochemistry course. And today we're going to talk about electrospray, we're going to talk about quadrupoles, we're going to talk about Orbitraps, and a few other mass analyzers. So, in contrast to MALDI, electrospray is quite different, where it takes a liquid stream that can come from chromatography or not, and it puts a voltage on that liquid stream and creates a spray, not unlike this spray seen here and in the image here, where this is the ion source of the mass spectrometer and this is the electrospray needle. And so what happens is that these the molecules within the liquid become charged, and they by being charged, and the liquid droplet starts to evaporate. And as the liquid evaporates, these charged molecules get pushed closer and closer together until they reach this point called the Rayleigh limit, where the charge density overcomes the surface tension of the droplet, and the droplet explodes. And so you end up with these charged ions in the gas phase that then move into the mass spectrometer. It was originally come up with in the mid to late 90s by John Fenn, who by that time had actually retired. His background was in supersonic expansion of gases. And so while he was emeritus in Yale, he came up with this idea of a soft ionization method to get biomolecules into the gas phase without destroying them. And this revolutionized mass spectrometry and revolutionized the measurement of biomolecules. Now, interestingly, John patented his technology. He didn't actually tell Yale University that he had done this. And when Yale University found out that he had patented it, they sued him to get the patent back. And it's probably one of the few instances of a Nobel Prize winner being sued by their own university for their invention. Now, one thing that I'd like to reiterate here is something that I've talked about in the other lectures, is that when we're talking about molecules, we're talking about a protein or a lipid, we're talking about thousands of molecules of exactly the same thing, and that becomes important. Now, in this particular case, the majority of the time we interface electrospray with reversed phase chromatography, which hopefully you've heard of in another one of your lectures. Reverse phase chromatography, you mainly have water or a organic solvent and acid. And so the hydrogen ions in the acid provide charge that goes onto these molecules to help them become ions. The water and the organic solvent mean that things are easily evaporated to create the electrospray. So electrospray, most importantly, creates multiply charged ions. So if we look at this solution structure here of, in this case, this is lysozyme. So in the top we have a space-filling model of all of the different atoms and where they would be. The bottom we have a ribbon structure showing what the structure of the protein would be. And here we have a space-filling model which has highlighted the basic residues, which would be positively charged under acid conditions. And what can happen is that different molecules of the same protein can take up different amounts of charge. So the mass spectrometer, as mentioned before, measures mass divided by charge ratios, and therefore a different molecule may have 8 positive charges, so the mass measured would be the mass of the protein divided by 8 charges, and you would get this mass here. Here's the mass with 9 charges, so you have a population of molecules that has 9 positive charges, 10 positive charges, 11 positive charges. And what you can also see under here is that when you look deeply into this charge state, you find that there are the isotopes of that charge state. So there are different molecules that all have 9 charges, but they have different numbers of C13 atoms in the molecule. We can calculate what the mass of the intact protein should be from these charge states by doing simultaneous equations. Now, I haven't put this up here for people to memorize. It's just to show you how this actually works. So this particular charge state has a mass of 1431.6. We don't know that this is a 10 plus ion. That's been done and put on there after the calculation has been done. So what we can do is we can use this and an adjacent charge state. We can put them into these simultaneous equations to work out what the mass would be of the protein with 1 charge. And then that gets deconvoluted to a spectrum like this, where we can calculate that in this case, lysozyme is 14,305.9 Daltons, and that was calculated by doing simultaneous equations on those charge states. So it's here that I should show you the real difference between MALDI, which we discussed in the last lecture, and electrospray, which we're talking about now. And so here we have myoglobin in both of these. In MALDI linear TOF, we get the 1 plus ion at 16,951. But in electrospray with time of flight, but in this case reflector time of flight, we get these individual charge states, which we can then deconvolute. We can assign what the charge state is to each one, and we can calculate what the mass of the intact protein is from those charge states. Electrospray is most typically coupled to quadrupole instruments to be able to manipulate the ions into other analyzers. So we're going to talk about quadrupoles now. Quadrupoles are a relatively simple device. They've been around for about half a century, and they are 4 rods arranged in a square typically. You can have 6, you can have 8, depending on the application. And these rods, you can apply voltage and radio frequency across these rods. The ions come in from the source through a lens as a beam, and depending on the voltage and the radio frequency, a certain mass ion will be allowed to pass out to the other end of the detector. This is shown in this diagram here, which comes from Agilent, where the collection of ions goes in at a certain voltage and radio frequency. Only the blue ions will pass of a certain mass. At a different radio frequency and voltage and radio frequency, these ions of a certain mass to charge ratio will pass. These certain ions of a mass to charge ratio will pass, and so on and so forth. You can only measure a single mass to charge rate. You can only transmit a single mass to charge ratio at a time to the detector. So the detector is just counting the number of ions that are being transmitted at a certain radio frequency and a certain voltage, and you calibrate the instrument to say if the detector measures ions at this voltage and this radio frequency, it is this mass. Now, you can scan quadrupoles, but while you're scanning, while this one is being transmitted to the detector, the rest of these are lost to the vacuum system. They get deflected, they don't get out of the other end of the quadrupole, and they get deflected. So while this one's being measured, these ones are not. While this one is being measured, this one is not, and neither are these two. So the scanning efficiency of a quadrupole is not very good, and this is why quadrupoles are typically used as ion transmission devices, not ion measuring devices. They are normally coupled to Orbitraps and TOFs. So there's some physics behind how these work, and again, all I'm doing here is scaring the crap out of you, and you shouldn't be committing these to memory. But what it shows is that the way that a particle moves within a quadrupole in a vacuum is dictated by these two laws. And you can combine these two equations to find out what the mass would be depending on the force applied, the acceleration, the electric field, and these other parameters. So this is how a quadrupole figures out what the mass to charge ratio of an ion is that hit the detector at a certain magnetic and electric field. Now, as I said, quadrupoles are not great for scanning mass ranges, but they are excellent for transmitting ions of a specific mass. So they are most typically for biomolecular analysis used in triple quadrupole instruments. And there was an image from the recent Tokyo Olympics which showed a room full of about 25 mass spectrometers based on this kind of technology. What it can do is that you've got a complex mixture of ions coming from the ion source, typically electrospray. Only one of those ions is transmitted to the collision cell where it's fragmented, and then one of the fragments is transmitted to the detector. So because the quadrupoles are really good at transmitting ions maximally of a certain mass, this works exceptionally well. It's the backbone of sports drug testing and illicit drug testing and so on and so forth. So that process that I just described is referred to as selection reaction monitoring. And you can think about it in protein and peptide work as doing a Western blot with a mass spectrometer, where a Western blot, you have an antibody that is specific for a particular protein. In this case, we tell the mass spectrometer what is the mass of a particular peptide from a protein that we want to measure, because antibodies typically only recognize a discrete part of a protein, not the whole protein. So the way that this works is that we ionize our peptides or our lipids or our metabolites from chromatography. We have a collection of molecules that are coming into the first quadrupole. Only one of these, the one that we tell it that we want to transmit, is transmitted to the collision cell, and it's fragmented. Multiple fragments are created, but we only measure one of those fragments at a time, then the next one, then the next one, then the next one. We're going to come back and talk about this in a lot more detail in a later lecture when I talk about applications. The great thing about using this kind of technology is that you can actually increase your sensitivity anywhere up to 1,000-fold. So you can really drill down into a sample to detect low abundance molecules and not see the other stuff that's around it. But you need to know what you are looking for before you start. So that's quadrupoles. In proteomics and discovery, lipidomics and metabolomics, typically you will use hybrid instruments where you have things like quadrupoles that are connected to orbitraps, where the quadrupole is used to select and transmit ions to a collision cell, or select and transmit a packet of ions into here where their mass is measured with high resolution. Similarly with a quad-TOF, where you have the selection quadrupole here, ions get transmitted through and then they get measured with high resolution in the time of flight detector, or they get fragmented and the fragments get measured by the time of flight detector. You can also have more elaborate hybrid instruments where you've got a quadrupole, you've got a different kind of multipole for selection and collision, and you've got an ion trap back here that can do different kinds of collision reactions or hold and trap ions to be sent back to be measured in the Orbitrap analyzer. So the first instrument that we're going to talk about is quadrupole time of flight. It's one of the oldest types of hybrid instruments. It's been around for a very long time, and this tutorial back in 2001 still gives you pretty much all you need to know about quadrupole time of flight. So I'm just going to show this video that comes from Agilent and talk over the top of it, if it plays. So the ions have been created by the ion source, and the different colors reflect different charge molecules. The gray ones are uncharged ions. There's no charge on those ions. They're being sucked out by the vacuum system. Because they have no charge, they can't be carried through the instrument. So the charged ions are now carried through the instrument. There's a number of ion guides that focus the ions as a beam in through the instrument. Now, in this particular case, what you're seeing in the quadrupole is that certain mass ions are not being transmitted. So only the green ions, whatever their mass to charge ratio is, they are being transmitted. Everything else is being sucked out by the vacuum system. They go into the collision cell and they're collided with nitrogen gas, and they're fragmented into their peptides. Now, this doesn't always happen. If you were just doing an intact scan, those molecules would just flow through the instrument as intact molecules. They wouldn't be fragmented. But to do MSMS, which we will talk about later, you need to fragment them. Again, they're focused, those fragments are focused down as a beam through this next ion guide, and then they go into what's called the pusher inside the time of flight tube. So once they get into the time of flight tube, they get pulsed orthogonally from the direction of going mainly from left to right, and they'll get pulsed upwards into the time of flight tube as shown here by the pulsar. And so you can see that you get certain packets of ions at a certain time pulsed, and that starts the clock on the time of flight. And so however long it takes from that pulse to the ions hitting the detector is related to the mass. So you can see different mass ions separating through the time of flight and then hitting the detector to be able to, so the detector registers it and registers, hang on, this was the start time, it's hit me here, that's the time, and therefore that is the mass as reflected there in the mass spectrum. Although in this case it's measuring the abundance, the continuing abundance of the same mass ions. So that's time of flight, very basically. The other really popular type of ion analyzer is called an ion trap. Now, a couple of years ago, I actually took these slides out because ion traps were not very popular anymore, and they weren't being used. But mainly because they had poor mass resolution, and so they weren't being used once things like the Orbitrap came into existence. However, they are useful. What they can do is they can accumulate a large number of ions to increase sensitivity before you do scans. And you can also fragment things and fragment them further, doing 3 rounds of mass spectrometry and so on. So these ion traps were brought back in instruments that Thermo make, like the Fusion. And so what we're going to do is I'm going to click out into a video from Thermo to look at an ion trap, and I'm just going to talk over this video. So here's the geometry of these instruments, where you've got your ion source over here. The ions come in from the chromatograph, and you'll see them being sprayed here. Those charged ions come down through this capillary into this series of lenses, where you try and filter out neutral molecules. So you can see this S-bend that the molecules have to go through, and they can only get through there if they're charged. You then have these ion gates where a packet of ions can be held within the trap, but any ions that are coming in can get stopped from coming in. And this happens on very, very short time frames. So this collection of ions of different masses, they get transferred into the back part of the ion trap, and then you excite the ions so that a certain mass ion will get ejected from the trap, because their ability to stay within the trap becomes more and more unstable. So it's related to their ion mass, and so they get spat out the side of the trap and into the detector. When you want to do MSMS, you can do the same thing where the ions are cooled, they're moved into the back of the instrument, and then the ions that you don't want to measure are thrown out of the trap because you don't want to fragment them. So in this case, we're exciting the ions to try and get rid of the ions that we don't want. In this case, we're getting rid of everything except the orange ions. And then the orange ions can then get moved into the back part of the trap where, they're getting fragmented here. So they're getting fragmented in this part of the trap. These are the fragments. They then can get moved to here where they are oscillated, and different fragment masses then get ejected out of the trap and into the detectors on either side, as you can see here. So the blue ions, they're unstable. They get thrown out of the trap and get measured because the radio frequency that they're ejected from the trap will tell you that a certain mass will get ejected at a certain radio frequency. So if the detector detects something hitting it at a certain radio frequency, it will say, oh, wait a minute, that molecule must be this mass. So now we'll return back to the slideshow and go on to our next slide, I think. There we go. And so the next thing that I want to talk about is ion cyclotrons, which is another form of another way of measuring the masses of ions. These have been around for a long time. They're not as prevalent as they used to be because they've been replaced a lot by the Orbitrap. But the reason that they're good is because they provide extremely high mass resolution. So once again, we have an ion source. We generate ions by electrospray, as you can see here, and you can see the charged droplet getting smaller and smaller and smaller and exploding so that you get charged ions going into the mass spectrometer. In this particular case, this instrument has a series of lenses, and in this case an ion trap where the ions can be accumulated before they get transferred into the ion cyclotron. In the ion cyclotron, it has opposing plates where you've got excitation electrodes and detection electrodes. And so the ions can move around within this electric and magnetic field, and they induce current in the detector plates depending on how they oscillate inside the cyclotron. So this ion here is creating a different kind of output in these detector plates than the others, and these are related to their mass. So what the raw data is that it looks like this. If we do Fourier transform, we can actually then turn that into a frequency diagram, and then we can turn that into a mass spectrum based on how the molecule induces current in these detector plates as they oscillate around inside the magnetic field. So So the way you measure mass to charge ratios in a cyclotron can be explained by this equation. And again, I don't want people to memorize these things. All I want to get across is that the mass resolution is proportional to the magnetic field strength. So the bigger the magnet, the more resolution that you can get, which is why you end up with 15 Tesla superconductors cooled with liquid helium. And the resolution is also proportional to the acquisition time. So the longer you acquire spectrum for, the higher the resolution you're going to get. And you can get up to millions of resolution. This part is actually important when we start to talk about orbitraps, which are essentially ion cyclotrons without the magnet. The ions in this case, they oscillate around this central electrode, and the current plates are either side of the trap. And as these molecules oscillate around the electrode, they induce the current that we talked about before. So, and you can again do Fourier transform to talk about to measure the mass of those molecules. Yet again, I'm going to go into YouTube and I'm going to bring up this video that I'm going to talk around. We're not going to watch the entire 5 minutes. So this is the inside of the Orbitrap, where you've got the ion transfer optics again. It does a 90-degree turn here so that neutral molecules can't go through. We have our quadrupole for doing ion selection, yet again, that we talked about before. We've got this part called the C-trap, which can move ions from different places in the machine. So we spray our molecules in. These are the charged ions. They go through this part of the machine to try and focus the beam a little bit better, and also to remove neutrals, which are unable to make this turn into the quadrupole. In this particular case, all of the ions are being transmitted from the quadrupole into the C-trap, and these will be transmitted from the C-trap into the analyzer, the Orbitrap, to do a full scan analysis. What is the intact mass of all of the molecules that is coming in at one particular time? So the oscillation causes this output, and then that output is transformed using Fourier transform into a mass spectrum, which gives really, really high accurate mass. The longer that you scan for, the more resolution that you can get. So now this will probably be looking at MSMS, which we will come back to again later on, but I might as well describe it now. So again, the molecules come in, they go through the quadrupole, and everything except the orange molecule gets spat out from the quadrupole from the vacuum system. These molecules move into what's called the HCD cell at the back of the instrument. So the quadrupole exit is here. This is the C-trap. This is the collision cell. And so you can collide these with nitrogen gas, making fragments which go back to the C-trap. The fragments then go into the Orbitrap, and the fragments get measured. Now remember, this is all occurring in a few milliseconds. Typically what we do is we set the machine to a maximum of 100 milliseconds per thing that we want to fragment. So I'll now return back to our regularly scheduled program and go back to the slides. So the next thing, the reason that I said before that ion traps weren't really being used that much anymore in proteomics and metabolomics and lipidomics was because of this instrument, the Q-Exactive platform, which we have one of these in the proteomics, lipidomics, metabolomics core facility, which just shows you how another reflection of what was in the video, where you've got your quadrupole mass analyzer, intact measurement, you go into the C-trap and into the Orbitrap. You can select a single molecule, fragment it in the collision cell, and measure the fragments in the Orbitrap. Now, the last two examples we've shown, the signal for detection is done by the analyzer itself, where the oscillation of the ions in an ion cyclotron and in an Orbitrap induces current into detector plates, which is measured, and then you do Fourier transform to turn that current into a mass spectrum. In time of flight and in quadrupoles, we typically replace those with either multi-channel plates or conversion diodes. So I'm just going to talk about those briefly at the end of the lecture here. So an electron multiplier is exactly what it sounds like, where you have an ion that comes in and it hits part of the detector, and that causes secondary ions to be emitted and hit different parts of the detector, increasing the number of electrons that are being produced until you get to the detector itself, where you can go from one ion to 1 million electrons to increase the signal that you're detecting. So this is signal amplification. It's not signal amplification in the way that you would consider PCR, but it does amplify signal quite considerably. So there's two types. This is a discrete diode where the different plates are separated from each other. This is a continuous diode where the electron surface and the creation of the electrons is continuous. And so these are typically found, these conversion diodes are typically found in triple quadrupole instruments. They're typically off axis to the ion beam, so that any photons or any neutral molecules that have managed to get it this far do not end up in the detector, giving you the wrong answer. So you can have these, off axis at the end of the detector, or in this case where you've got a SciX 55 or 6500 system where you have Q1, your selection quadrupole here, but the collision cell actually bends back 180 degrees so that anything that's neutral shouldn't be able to make this turn. You've got your third collision cell, and then the detector is off axis as well. So the ions have to be charged to get sucked into that detector so that you're not detecting neutrals, which can lead you down the garden path. The other type of detector is these microchannel plates, which can be considered as a continuous diode. And these typically are at the back of TOF tubes. And so you end up with an ion hitting the first one, creating a cascade of electrons through these plates, creating a further cascade of electrons, which then hit the detector and create a signal that you can measure. And so the mass of the ion is determined by how long it took from the pulse to the signal at this anode. And so this can be shown in these series of slides that was made by a good friend of mine, Sarah Kruger from AB SciX, who's no longer with SciX, she's moved on. And what we see is that we're measuring time, and we're measuring the number of ions that hit the detector at a particular time. We talked about this with in the last lecture with Maldi and Toff. So every 0.5 of a second, we measure the number of ions that are hitting the detector. So we get this peak that's created, and the center of that peak is whatever the mass of the peptide is. So under this mass here is a series of scans of increasing ion intensity at a particular moment in time. And so this is C12, this is C13, 2 C13s, 3 C13s. A conversion diode is typically found in ion trap-based instruments, where we said that in the trap you vary the radio frequency, and at a certain radio frequency a certain mass ion no longer wants to be in the trap, and it gets spat out and detected by these conversion diodes. So the ions hit this and cause secondary emission of electrons, which then get detected by this part of the detector, and you measure a signal of intensity. Now, the last point that I want to make before I end the lecture is this idea of mass calibration, because what all that I've talked about before relies on the mass spectrometer being told what the mass of an ion is. So a time of flight tube needs to know that if an ion is pulsed and it hits the detector after a certain time, it is X mass. And the way that you do that is you do it by known standards where you calibrate the mass range. And so TOFs need to know flight time. Quadrupoles and ion traps need to know that at a radio frequency and a DC voltage, if you detect an ion at the detector, it must have been this mass because it is what would be transmitted. And orbitraps are the same. They need to know the frequency of the oscillation that refers to a particular mass. And so you do this by calibration routines. So that brings me to the end. So what we have talked about in this video is how electrospray ionization works. It is probably the most prevalent way of getting ions into a mass spectrometer. And the reason for that is it can be easily coupled with reverse phase chromatography to reduce the complexity of samples that are going into the mass spectrometer to be analyzed. And this is something that we'll talk about in a later lecture. Modern instruments typically are hybrids of different mass analyzers. So you combine multiple quadrupoles together, or a quadrupole with a time of flight detector, quadrupole with an orbitrap, or with linear ion traps. In the next lecture, we're going to spend some time talking about a recent addition to mass spectrometry, that of ion mobility. And it's become so important over the last couple of years that it needs our attention. And so we're going to talk about that next.